For decades, we have been told that Mars is humanity's destiny, that within our lifetimes, perhaps within the next decade, we will establish permanent settlements on the red planet. Bold predictions promise cities, terraformed landscapes, even families born beneath Martian skies. The images are inspiring: gleaming habitats, astronauts striding confidently across rusty plains, gardens growing under dome-filtered sunlight. Yet behind these visions lies a labyrinth of technical, biological, and physical challenges so profound that many scientists quietly wonder not if a Mars colony would fail, but when and how catastrophically. This is not a story about dreams deferred or ambitions crushed. It is a story about reality meeting imagination, about the invisible barriers that separate a successful 3-week Apollo mission from a sustainable multi-year colony on another world. The distance between Earth and Mars is not simply measured in miles, but in the thousands of interlocking systems that must function perfectly, simultaneously, indefinitely, with no margin for error and no possibility of rescue. Most people imagine Mars colonization faces obvious challenges: rocket fuel, food supplies, boredom. These are real concerns, but they are only the surface. Beneath them lies a darker catalogue of threats that rarely appear in promotional videos or mission statements. The radiation that silently shreds DNA with every passing hour. The dust so fine it penetrates every seal, abrading machinery and infiltrating lungs. The psychological weight of knowing that if anything goes critically wrong, Earth is not 20 minutes away by ambulance, but 20 months away by spacecraft, if a rescue mission could even be mounted at all. Tonight, we will explore these hidden obstacles with the detail they deserve. Not to discourage exploration, but to honor it with honesty. To understand that failure is not the opposite of progress, it is often the necessary precursor. Every challenge we examine, from water extraction to medical emergencies, from power generation to the simple act of growing food, reveals layers of complexity that transform Mars colonization from an engineering problem into something closer to a cosmic gamble. If you enjoy these deep explorations into the realities behind our greatest ambitions, please consider liking this video and subscribing. Your support allows us to continue investigating not just what we hope to achieve, but what it will truly take to get there. Now settle in. Let your mind drift across that vast distance to a world where the sky is pink. Gravity is a third of Earth's, and every breath depends on technology functioning flawlessly in an environment that wants nothing more than to reclaim the silence. Before we begin our journey through the specific systems that would face collapse, I would love to know where you are right now. What part of Earth are you watching from? What time is it there? Drop a comment below. It is humbling and beautiful to know that while we explore the challenges of reaching Mars, we are connected here, across continents and time zones, by curiosity alone. Let us begin with the threat you cannot see, cannot feel, and cannot escape. The invisible rain of radiation that falls constantly on Mars, patient and merciless. Mars appears serene from orbit, a rusty world painted in ochre and amber, quiet beneath its thin veil of atmosphere. But this silence conceals a truth that makes Mars one of the most hostile environments humanity has ever considered inhabiting. Unlike Earth, which bathes beneath a protective magnetic shield generated by its churning iron core, Mars stands naked before the cosmos. Its magnetic field died billions of years ago when the planet's interior cooled and solidified. What remains is a world exposed, vulnerable to an invisible storm that never ceases, a radiation environment so severe It could unravel human biology itself within the first year of colonization. On Earth, we are shielded. Our planet's magnetosphere deflects the solar wind, streams of charged particles that erupt from the sun with unimaginable violence. Galactic cosmic rays, the high-energy remnants of exploded stars from across the galaxy, are also bent away from our surface by this invisible barrier. The atmosphere provides additional protection, absorbing what little radiation penetrates through. Standing on Earth's surface, we receive approximately 3 millisieverts of radiation per year from natural sources. Astronauts aboard the International Space Station, orbiting above much of the atmosphere but still within Earth's magnetic embrace, receive roughly 144 millisieverts annually. This is considered manageable, monitored, within acceptable limits for career exposure. Mars offers no such mercy. On the Martian surface, colonists would face approximately 250 millisieverts per year during quiet solar periods, more than 80 times Earth's natural background radiation. But this average figure conceals the true danger. Mars is subject to solar particle events, sudden eruptions of high-energy protons released during solar flares and coronal mass ejections. These events are unpredictable, violent, and potentially lethal. A single major solar particle event could deliver radiation doses exceeding what is considered safe for an entire lifetime in just hours. Without warning, without shelter, the first colonists could face acute radiation syndrome, the same conditions suffered by victims of nuclear accidents, nausea, disorientation, cellular collapse. The DNA within every cell of the human body would become a target. Galactic cosmic rays, composed of particles accelerated to nearly the speed of light, possess enough energy to tear through spacecraft walls, habitat modules, even human tissue, leaving trails of ionized destruction in their wake. Unlike the radiation from X-rays or gamma rays, which deposit energy in a single point, cosmic rays create cascading damage along their path, shattering DNA strands, triggering mutations, overwhelming the cell's natural repair mechanisms. Over months, the cumulative effect becomes catastrophic. Cancer rates would climb dramatically. Current models suggest that a 2-year mission to Mars and back would give astronauts a 5% increased lifetime risk of fatal cancer. For permanent colonists spending their entire first year on the surface, the risk multiplies. Proposed solutions exist, but their adequacy during the fragile early colony phase remains deeply uncertain. Shielding requires mass. The more material between a person and space, the greater the protection. Water is often suggested as ideal shielding, hydrogen-rich and effective at absorbing radiation. Ice could be harvested and used to line habitat walls. Regolith, the Martian soil itself, could be piled atop structures, creating buried sanctuaries. But these solutions demand time, infrastructure, and energy, resources that a struggling first-year colony may not possess. The initial habitats, transported from Earth, would likely be lightweight by necessity, designed for efficient launch and landing, not for radiation protection. Colonists would arrive to find themselves living in thin-walled shelters, exposed, counting the days until adequate shielding could be constructed. Even if construction proceeds without delay, building underground habitats or covering surface structures with sufficient regolith is a monumental engineering challenge. Heavy equipment must function in low temperatures, thin atmosphere, and fine abrasive dust. Excavation into Martian rock requires drilling and explosives. Every delay, every equipment failure, every unforeseen complication extends the period of vulnerability. During this window, measured not in days, but potentially in months, the colonists remain at risk. A single solar particle event during this construction phase could force the entire crew into inadequate emergency shelters, huddled together, hoping the walls are thick enough, knowing they may not be. But the threat is not limited to cancer and cellular damage. Recent research suggests that radiation exposure affects the brain in ways we are only beginning to understand. Studies on rodents exposed to galactic cosmic ray analogues show significant cognitive impairment, reductions in memory, learning capacity, and decision-making ability. Neurons are damaged. Neural networks are disrupted. The very cognitive functions required to operate a colony, to troubleshoot problems, to make rapid critical decisions under pressure, may be compromised by the radiation environment itself. Imagine a colony where every member is slowly losing their mental edge, where reaction times lengthen, where clarity of thought becomes elusive. In an environment where a single mistake can cascade into disaster, cognitive impairment is not merely a health concern. It is an existential threat to the entire mission. The comparison with the ISS is instructive but deceptive. The ISS orbits within Earth's protective magnetic field, benefiting from shielding that Mars simply does not provide. Even so, astronauts on the ISS are carefully monitored, their missions limited in duration to manage cumulative exposure. Mars colonists would have no such luxury. There is no rotation schedule, no return flight waiting in a few months. The radiation is relentless, accumulating day after day, and the colonists must endure it while simultaneously building, exploring, and surviving in an alien environment. Perhaps the most unsettling aspect of Mars's radiation environment is its invisibility. Colonists would not see the cosmic rays penetrating their bodies. They would not feel the DNA breaking apart inside their cells. There would be no alarm, no warning light, only the slow, silent accumulation of damage, hidden beneath the surface of ordinary days. Radiation does not announce itself until the harm is already done, until the cancers begin to form years later, until the cognitive decline becomes undeniable. The radiation nightmare is not a failure of will or technology. It is a fundamental challenge posed by a dead planet that has lost its shield. Mars stands exposed before forces that have raged since the birth of stars, and humanity, fragile and biological, must find a way to survive in that unforgiving light. On Earth, dust is an inconvenience. On Mars, dust is an adversary that never rests, never retreats, and never forgives. The Martian regolith, that fine powder covering the planet's surface, is not merely soil waiting to be cultivated. It is a silent destroyer, a substance so unlike anything we encounter on Earth that our very biology recoils from it. This is not the comforting dirt of a garden or the annoying grit that accumulates on a windowsill. This is a material forged in conditions utterly foreign to life, and it carries with it a chemical signature that makes it fundamentally hostile to human existence. The first challenge reveals itself at the molecular level. Martian regolith contains perchlorates, compounds of chlorine and oxygen that exist in concentrations up to 1% by weight across much of the planet's surface. On Earth, perchlorates are considered toxic substances, carefully regulated and restricted. They interfere with thyroid function, disrupting the body's ability to absorb iodine and regulate metabolism. Prolonged exposure can lead to thyroid disease, developmental issues, and potentially neurological damage. Yet on Mars, this toxic substance permeates the ground everywhere, mixed intimately with every grain of dust that covers the planet. Imagine arriving at your new Martian habitat after a surface exploration mission. You cannot simply step inside. Every surface of your spacesuit is coated in regolith. Every fold of fabric, every seal, Every joint holds particles that want nothing more than to follow you indoors. The astronauts of the Apollo missions described lunar dust as one of their most persistent challenges, but Martian dust presents problems that moon dust never could. Where lunar regolith is jagged and abrasive from billions of years of micrometeorite impacts, Martian dust has been weathered by ancient winds into particles so fine they make talcum powder seem coarse by comparison. These particles measure just a few micrometers across, small enough to slip through the weave of fabric, small enough to infiltrate seals designed to withstand vacuum, small enough to become airborne at the slightest disturbance. But size alone does not explain the insidious nature of Martian dust. The regolith carries an electrostatic charge generated by friction with the planet's thin atmosphere and bombardment by solar radiation. This charge causes the dust to cling to surfaces with surprising tenacity, adhering to metal, plastic, and fabric alike. It does not simply fall away when you brush it off. It resists, clinging stubbornly, working its way into every crevice and gap. The Apollo astronauts could taste lunar dust in their capsules, could smell its acrid odor described as reminiscent of spent gunpowder. They reported irritated eyes and respiratory discomfort, even after brief exposures. On Mars, the problem would be orders of magnitude worse. Martian dust particles are smaller, more abundant, and chemically reactive in ways lunar dust never was. If even microscopic amounts enter the habitat's atmosphere, colonists would breathe them in with every breath. These particles would penetrate deep into lung tissue, far beyond the reach of the body's natural defenses. The human respiratory system evolved on Earth to handle certain types of particulate matter. Mucus, cilia, and immune responses work together to capture and expel foreign particles. But Martian regolith is angular at the microscopic level despite its fine texture, sharp enough to cause mechanical damage to delicate lung tissue. More concerning still, the perchlorates coating each particle would begin to interact with the moist environment of human lungs, potentially creating chemical reactions that could inflame tissue and compromise respiratory function over time. Some researchers have suggested that chronic exposure could lead to conditions resembling silicosis, the devastating lung disease that afflicts miners who breathe crystalline silica dust. Equipment suffers alongside human biology. Every mechanical system brought to Mars must contend with dust infiltration. Solar panels, essential for power generation, lose efficiency as dust accumulates on their surfaces, blocking precious sunlight. Rovers have experienced this firsthand. Some Martian dust storms have reduced solar panel output by 90% or more, leaving machines to hibernate in darkness, hoping that clearing winds might eventually sweep away enough particles to restore function. For a habitat dependent on consistent power, such losses could cascade into system-wide failures. Seals represent a particular vulnerability. Every door, every hatch, every connection point between modules must maintain perfect integrity against the Martian environment. Yet regolith works its way into these seals with relentless persistence. The particles are abrasive, harder than many materials we use for gaskets and O-rings. Each time a seal compresses, dust particles grind against the seal material, slowly wearing it down. Over months and years, micro cracks form, and what began as perfect containment gradually degrades into potential catastrophic failure. A seal that fails could mean explosive decompression, or at minimum, the slow leak of precious breathable atmosphere into the Martian void. Decontamination becomes an obsession, yet remains perpetually incomplete. On Earth, we wash away dirt with abundant water. On Mars, water is the most precious resource imaginable, extracted laboriously from ice or pulled molecule by molecule from the thin atmosphere. Using liters of water to wash dust from spacesuits after every surface expedition would deplete reserves that are needed for drinking, food production, and oxygen generation. Alternative decontamination methods, perhaps using compressed CO2 or electrostatic repulsion systems, would need to be developed and proven reliable. But no system can achieve perfect cleanliness, and good enough on Mars might mean the slow accumulation of toxic dust in living spaces, building up in air filters, settling on surfaces where colonists eat and sleep. The agricultural implications alone could doom a colony. Growing food on Mars requires creating soil from Martian regolith. But how does one detoxify millions of particles contaminated with perchlorates? Some research suggests that certain bacteria could potentially break down these compounds, converting them into harmless chlorides. But establishing such bioremediation systems would take time, require careful cultivation of microbial colonies, and demand resources that a first-year colony might not be able to spare. Meanwhile, any contamination of crops with untreated regolith could introduce perchlorates into the food supply, poisoning the very sustenance colonists depend upon. Consider the psychological burden this creates. Every moment outside the habitat means returning with an invisible coating of toxic dust. Every surface exploration, every maintenance task, every scientific expedition ends with the knowledge that you are bringing danger back with you. Meticulous cleaning becomes not just a chore, but a survival ritual, performed with the awareness that any lapse could have consequences. The dust becomes an omnipresent anxiety, a reminder that Mars does not welcome human presence and will exploit every opportunity to infiltrate the fragile bubbles of Earth-like environment we try to maintain. Some might ask whether technological solutions could mitigate these challenges. Perhaps advanced materials could create perfectly sealed habitats and suits. Perhaps automated systems could handle all exterior work, eliminating human exposure. Perhaps future innovations could render the dust problem manageable. These possibilities deserve consideration, but they remain theoretical. The first Martian colony would work with technologies available now or in the near future. And current materials, science offers no perfect solution to the combination of ultrafine particles, electrostatic adhesion, and chemical toxicity that Martian regolith presents. The dust that never settles is perhaps the most insidious challenge a Martian colony would face because it is constant, unavoidable, and cumulative. Unlike a sudden equipment failure or medical emergency, dust degradation happens slowly, grain by grain, breath by breath. It does not announce itself with alarms or obvious symptoms until damage has already occurred. By the time respiratory problems manifest, by the time seals begin to fail noticeably, by the time equipment malfunctions become frequent, the colony may already be caught in an irreversible decline. Mars holds its dust close, and that dust carries with it a simple message. This world was not made for you. Every particle is a reminder that human biology evolved for Earth, and Earth alone. To live on Mars would mean living in perpetual opposition to the very ground beneath our feet, fighting a battle against an enemy too small to see, but too persistent to ever truly defeat. Mars greets its visitors with an atmosphere so thin it might as well not exist. At just 0.6% of Earth's atmospheric pressure, the Martian surface is closer to the vacuum of space than to any environment humanity has ever called home. Standing on the surface of Mars without protection, the pressure would be roughly equivalent to standing at an altitude of 100,000 feet above Earth's surface, more than 3 times higher than any aircraft typically flies. At this pressure, human blood begins to boil at body temperature. This is not a metaphor. It is a physical reality called ebulism. Water in the tissues vaporizes. The body expands. Death comes not from suffocation alone, but from a cascade of failures as the human form confronts conditions it was never designed to endure. For a Mars colony to survive even a single day, its inhabitants must live permanently inside pressurized habitats, artificial bubbles of Earth-like conditions surrounded by an environment inherently hostile to their existence. These structures become more than shelter. They become the only barrier between life and the void. Every wall, every seal, every airlock represents a single point of failure between survival and catastrophe. Consider for a moment what this truly means. On Earth, a leak in a building is an inconvenience. A crack in a wall requires repair, but poses no immediate threat to life. On Mars, any breach in a habitat's pressure vessel initiates a countdown. Air begins rushing outward into the near vacuum. Pressure drops. Oxygen depletes. The inhabitants have minutes, perhaps only seconds, to identify the breach, seal it, and restore pressure before the habitat becomes uninhabitable. There is no opening a window for fresh air. There is no stepping outside to assess damage. Every response must occur from within the failing structure itself, while alarm systems blare and pressure gauges fall towards zero. The engineering challenges are profound and unforgiving. A habitat on Mars must maintain an internal pressure difference of nearly 15 pounds per square inch compared to the outside environment. This differential places enormous stress on every square foot of the structure's surface. Imagine a balloon inflated to its limit, except this balloon must remain inflated for years, decades even, without failure. The materials must be strong enough to contain pressure, light enough to transport from Earth, and resilient enough to withstand temperature swings of more than 100 degrees Celsius between Martian day and night. They must not become brittle in the cold, nor weakened by ultraviolet radiation that penetrates Mars' thin atmosphere without mercy. The fatigue accumulates silently. Each pressurization cycle, each temperature fluctuation, each tiny expansion and contraction of the habitat walls creates microscopic stress fractures in the material. Over months and years, these fractures grow. What begins as an imperfection invisible to the naked eye becomes a weak point, and weak points become failures. Engineers call this pressure differential fatigue, the slow degradation of materials under constant stress. On Earth, we can monitor structures for decades, replacing components before they fail. On Mars, every replacement part must either be manufactured on site with limited resources or shipped from Earth at extraordinary cost and delay. The question becomes not if a habitat will develop failures, but when and whether those failures can be detected and repaired before they become catastrophic. And then there is the environment itself, actively working against these fragile structures. Micrometeorites, tiny fragments of rock traveling at thousands of miles per hour, regularly impact the Martian surface. Without a thick atmosphere to burn them up, as happens on Earth, these particles strike with full force. Most are small, grain-sized, but even a grain-sized impact at hypersonic velocity can puncture materials not designed to withstand such forces. A single micrometeorite striking a habitat wall could create a breach faster than any automated system could respond. The colonists inside might have only moments to seal themselves in an interior compartment, hoping that the puncture is small enough to be patched before all breathable air is lost. Dust storms on Mars, which can envelop the entire planet for months, present a different kind of siege. The fine, abrasive particles, charged with static electricity, infiltrate every mechanism, clog every filter, and sandblast every exposed surface, while the winds themselves are not strong enough to topple structures due to the thin atmosphere. The relentless accumulation of dust can obscure solar panels, reducing power generation to dangerous levels. It can jam airlocks, preventing both entry and exit. Most insidiously, it can work its way into the seals that maintain pressure integrity, creating pathways for slow leaks that drain a habitat's atmosphere molecule by molecule, so gradually that they might go undetected until it is too late. Living in such an environment exacts a psychological toll that is difficult to overstate. Every colonist would know with absolute certainty that only a thin wall separates them from death. This is not paranoia, it is reality. Sleep would come with the knowledge that a failure could occur at any moment, that an alarm might sound in the middle of the night, signaling depressurization. Every creak of the habitat structure, every unfamiliar sound, every fluctuation in pressure readings becomes a potential harbinger of disaster. The mind, evolved to find safety in shelter, can find no true rest when the shelter itself is so fragile. Then there is the matter of extravehicular activity, of venturing outside the habitat in a pressure suit. EVA suits on Mars would need to be marvels of engineering, maintaining Earth-like pressure while allowing mobility in an environment that wants nothing more than to equalize that pressure with the near vacuum outside. Every EVA would be a calculated risk. Suits develop wear. Seals degrade. Joints that flex repeatedly develop weak points. A torn glove, a failed seal, a puncture from a sharp rock. Any of these could initiate rapid decompression. Unlike on the International Space Station, where fellow crew members can quickly assist during an EVA emergency, a colonist on Mars might be minutes or hours away from the nearest airlock. By the time rescue arrives, the mathematics of pressure loss may have already written the outcome. Perhaps most troubling is the impossibility of quick response. On Earth, emergency services can reach most locations within minutes. On Mars, a colonist in distress during an EVA is fundamentally alone, even if the habitat is nearby. Donning another pressure suit, cycling through the airlock, and reaching the victim takes time. Time that might not exist when pressure is bleeding away into the Martian atmosphere. The colony could do everything right, maintain perfect equipment, follow every protocol, and still lose people to the simple, inescapable reality that humans were never meant to exist in a place with no air. The atmospheric pressure of Mars is not merely a technical challenge to be solved with better engineering. It is a fundamental incompatibility between human physiology and the Martian environment. Every moment of every day, the colonists would exist in defiance of the planet's insistence that they should not be there. The thin walls of their habitat would be all that stands between intention and extinction. Living on Mars means living in a permanent state of emergency that simply hasn't happened yet, where the difference between survival and catastrophe is measured in millimeters of material and seconds of response time. Here, in this near vacuum, we confront an uncomfortable truth. Some environments do not merely challenge human survival, they fundamentally oppose it. Water is life. On Earth, this truth is so fundamental we barely notice it. Rivers flow, rain falls, oceans cover 3/4 of our world. Water is everywhere, constantly recycled through evaporation and precipitation, purified by natural systems refined over billions of years. But on Mars, water tells a different story. It is not abundant, it is not flowing, it is locked away, hidden beneath layers of dust and ice, transformed into something closer to stone than liquid. And yet, without it, no colony can survive even a single month. The search for water on Mars begins with a paradox. We know Mars has water. Satellites orbiting the red planet have confirmed vast deposits of ice at the poles, buried glaciers in the mid-latitudes, and subsurface ice scattered across regions that appear, from above, as nothing more than barren plains. Some estimates suggest there is enough water ice on Mars to cover the entire planet in a liquid ocean over 100 feet deep. But knowing water exists and actually accessing it are separated by a chasm of engineering, energy, and time that no first-year colony could hope to bridge. The most accessible water ice lies beneath the surface in regions called the mid-latitudes, roughly between 30 and 60 degrees north and south of the Martian equator. Here, radar imaging from orbiters like Mars Reconnaissance Orbiter has detected ice deposits buried beneath just a few feet to several yards of regolith. To human eyes standing on the surface, these regions would appear unremarkable, dusty plains stretching to the horizon, no different from 1,000 other desolate Martian landscapes. But beneath the rust-colored soil lies frozen water, preserved in darkness, waiting. Yet even in these optimal locations, extracting water is not as simple as digging a hole and melting ice. The regolith must first be removed, a process requiring excavation equipment, energy for operation, and constant maintenance against the abrasive Martian dust. Once exposed, the ice must be heated to convert it into liquid water, a process that demands immense energy in an environment where temperatures routinely plunge to -80 degrees Fahrenheit at night. On Earth, melting ice is trivial. On Mars, every litre of water extracted represents kilowatts of precious power diverted from life support, heating, and communication systems. The energy requirements alone are staggering. To melt 1 kilogram of ice on Mars requires approximately 334 kilojoules of energy, just to change its state from solid to liquid. But the ice is not sitting at 0 degrees Celsius. It is frozen solid at temperatures far below the melting point, meaning additional energy must first warm the ice before melting can even begin. Conservative estimates suggest that producing just 100 litres of water per day, enough for basic drinking and hygiene for a small crew, could consume more than 10% of a colony's total energy budget. And this is before purification, before distribution, before any water is used for agriculture or oxygen production. Even if the ice can be melted, the resulting water is not pure. Mars's soil is saturated with perchlorates, toxic chemical compounds that pose serious health risks to humans. Perchlorates interfere with thyroid function, disrupt hormone regulation, and in high concentrations can be lethal. Water extracted from Martian ice carries these contaminants, dissolved into the liquid as the ice melts. Purification systems must remove not only perchlorates, but also sulfates, chlorides, and other minerals that make Martian water, in its raw form, undrinkable. Advanced filtration, reverse osmosis, and chemical treatment are all necessary, each system adding weight, complexity, and points of failure to an already fragile infrastructure. On Earth, water recycling systems aboard the International Space Station recover approximately 90% of water from waste and humidity. This is considered an engineering triumph, the result of decades of refinement and constant resupply of replacement parts. On Mars, a first-year colony would need to match or exceed this efficiency with no resupply, no backup systems flown in from Earth, and no margin for error. But even at 90% efficiency, losses are inevitable. Every shower, every meal preparation, every use of water for hygiene or agriculture results in a small percentage lost to the Martian environment, absorbed into equipment, vented as vapor, or chemically bound in reactions that render it unrecoverable. Over weeks and months, these losses accumulate. A colony that begins with 1,000 litres of water could, through inefficiencies and inevitable system degradation, find itself with less than 500 litres within 6 months. The competition for water becomes a brutal calculus of survival. Humans need approximately 2 to 3 litres per day for drinking alone, more in the physically demanding environment of Mars. Hygiene, essential for preventing illness in a confined space, requires additional water. Agriculture, necessary to supplement food supplies and provide psychological relief through the presence of living plants, demands water in quantities that dwarf human consumption. A small greenhouse growing lettuce and tomatoes could easily consume 50 to 100 litres per day. And then there is the ultimate competitor, rocket fuel. Water is not just life support on Mars, it is propellant. Electrolysis can split water into hydrogen and oxygen, the fundamental components of rocket fuel. For a colony that hopes to return to Earth or even launch supply missions between Mars settlements, water becomes the currency of travel. Every litre of water diverted to fuel production is a litre taken from drinking reserves, from agriculture, from the systems that keep humans alive. The choice is not academic, it is existential. Do you drink the water, or do you prepare for the possibility of escape? The timeline for establishing sustainable water infrastructure reveals the impossibility of first-year success. Consider the sequence of necessary achievements: landing with or building excavation equipment, locating and accessing ice deposits, constructing melting facilities, establishing purification systems, creating distribution networks, and implementing recycling technology, all while maintaining existing water reserves transported from Earth. Each step requires months of work, testing, and troubleshooting. Equipment breaks, filters clog, pumps freeze, and every failure consumes time that the colony does not have. Some propose drilling for deeper aquifers, liquid water that may exist miles beneath Mars's surface, heated by geothermal energy and protected from the frozen surface conditions. These hidden reservoirs, if they exist, could hold more water than all the polar ice combined. But drilling technology capable of penetrating miles of Martian rock does not exist in portable, reliable forms. The deepest drilling on Mars, conducted by rovers, has reached mere inches. The gulf between inches and miles is not just technical. It is a fantasy that belongs to the second or third generation of Martian infrastructure, not the desperate first year of survival. Perhaps most troubling is the uncertainty itself. Satellite data shows where ice likely exists, but likely is not the same as confirmed. A colony could land in a region chosen for its supposed ice deposits, only to discover that the ice is deeper, more contaminated, or less abundant than predicted. On Earth, such miscalculations are inconvenient. On Mars, they are catastrophic. Water is not a resource that can be improvised. It cannot be synthesized from Martian air in quantities sufficient to sustain life. Without water, the human body fails within days. Without water, every other system, agriculture, oxygen production, radiation shielding through ice barriers, becomes irrelevant. The water crisis on Mars is not a problem to be solved. It is a reality to be endured. Every litre must be accounted for, rationed with precision that leaves no room for waste, no space for comfort. Showers become memories. Laundry becomes impossible. Agriculture shrinks to the bare minimum necessary to supplement nutrition. And still, the losses continue, invisible and inevitable, slowly draining the colony's reserves while the machinery labors to extract more from the frozen, toxic ground. To journey to Mars is to enter a world where water, the most fundamental element of life, becomes the rarest treasure. The colony does not fail because water does not exist. It fails because accessing, purifying, and sustaining water demands resources, time, and reliability that no first-year settlement can provide. In the rust-colored deserts of Mars, water is not a gift. It is a siege that never ends. Food on Mars is not grown in fields. It is engineered in bubbles. From orbit, the first colony looks like a scattering of pale domes pressed into the rust-red dust, as if someone tried to plant a greenhouse on the bottom of a dead ocean. Inside those domes, beneath white LEDs and dripping condensers, lies the most fragile part of the entire settlement. Not the airlocks, not the reactors, the salad. On Earth, food is everywhere and invisible at the same time. We walk past cornfields without seeing the years of breeding behind each stalk. We open a refrigerator without thinking about the thousands of miles of logistics that quietly restock it. On Mars, none of that exists. Every calorie is counted. Every leaf is measured in oxygen, water, and time. Before anyone can plant a seed in Martian ground, they must confront an invisible toxin embedded in the soil itself. Mars dust is not dirt the way we know it. It is a chemical minefield. Mixed through its fine grains are perchlorates, salts that, on Earth, are used in fireworks and rocket fuel. On Mars, they occur naturally, formed over millions of years by ultraviolet radiation breaking down chlorine-bearing minerals. To human biology, these compounds are not just inconvenient, they are poisonous, interfering with the thyroid, damaging organs, and disrupting metabolism. So the first step in growing food is not sowing, it is cleansing. Soil must be collected, filtered, and washed again and again to leach out perchlorates. That takes water, which is already the colony's most guarded resource. Then it must be heated or biologically treated, using specially selected microbes that can break the perchlorates down into safer compounds. Each method adds complexity. Each method adds equipment that can fail. On Earth, a farmer can walk into a field, press a seed into the ground, and trust that the planet has already done most of the work. On Mars, turning regolith into something that even resembles soil is a months-long industrial process. The first Martian gardens are less like farms and more like chemical plants wearing green. And while that soil is slowly being transformed, something else is missing: sunlight. Mars orbits farther from the Sun than Earth. At that distance, the solar energy bathing the planet is roughly 40% weaker. On a clear day, noon on Mars might feel like a hazy Earth morning. For humans, this is simply dim. For plants, it can be the difference between growth and starvation. Plants are solar engines. They transform light into sugars with ruthless efficiency. But they are also stubborn. Many crops evolved under Earth's bright skies and respond poorly to weaker illumination. To compensate, Martian greenhouses must capture and amplify every photon they can. Transparent domes, reflective walls, high-efficiency LEDs tuned to the exact wavelengths chlorophyll craves, red and blue, become not luxuries, but necessities. Yet every extra photon of artificial light has a cost. LEDs demand electric power. Power requires reactors, solar fields, batteries, or fuel cells. Every kilowatt sent into the greenhouse is a kilowatt not available for life support, communications, or heating. There is a quiet race beneath those glowing panels, the race between growing food and running out of the energy needed to grow it. Time, too, is an unforgiving participant in this race. When the first crew lands, they arrive with food, dehydrated packets, vacuum-sealed pouches, powdered nutrients, enough to last for months, perhaps a year, if rationed carefully. The hope is that by the time those supplies dwindle, the first harvest will be ready. But plants do not care about mission timelines. Lettuce might offer leaves in a few weeks, radishes perhaps in a month. But staples, wheat, potatoes, soybeans, take much longer. 80, 90, 100 days from planting to harvest, assuming everything goes well. And on Mars, everything goes well is a fragile assumption. Seeds must germinate in unfamiliar gravity. Pumps must circulate water precisely through hydroponic channels. CO2 levels must be balanced so plants can photosynthesize without being poisoned. A single clogged filter, a miscalibrated pump, a fungal outbreak in the nutrient solution, and an entire growth cycle can stall or be lost. Each failed crop does not just mean no salad. It means the colony's countdown clock to empty storage ticks faster. There is also the question of how much food is truly enough. In Mars's weaker gravity, you weigh less, but you do not become less alive. The human body still needs energy to stay warm in cold habitats, to maintain muscle that is constantly trying to atrophy in the lesser pool, to run life support systems embedded in clothing and equipment. Some analyses suggest that settlers may need equal or even slightly higher caloric intake than on Earth, simply to counter muscle loss, bone density decline, and the extra exertion of working in pressurized suits and confined spaces. If an average person on Earth lives comfortably on 2,000 calories a day, a Mars colonist working in these conditions might need more. Now place those numbers alongside the realities of Martian agriculture. Even optimistic projections for advanced greenhouse systems suggest that achieving Earth-like yields per square meter will be challenging. Light is weaker, water is scarce, pollinators are absent. Every plant sits at the end of a long chain of engineering, and any link in that chain can break. In that mismatch between what bodies need and what a young Martian farm can deliver lies a dangerous gap. On Earth, much of agriculture is invisible help. Bees drift from flower to flower, carrying pollen with the quiet confidence of millions of years of evolution. Wind stirs grasses and trees, scattering pollen grains in invisible clouds. Birds and insects knit together ecosystems in ways no single person has to plan or understand. On Mars, the wind is too thin, and the bees are thousands of miles away on a blue dot in the sky. Pollination becomes a human task. Tomatoes, peppers, squash, many crops rely on transferring pollen from one flower to another to bear fruit. In a sealed habitat, this might be done by hand, using tiny brushes or gentle vibrations. It is delicate work, time-consuming and unforgiving. A crew already stretched thin with maintenance, science, construction and survival must now also become full-time gardeners and pollinators. Perhaps robots will help. Perhaps electric toothbrushes buzzing along stems will mimic the buzz of bees. But every added system is another device that must function perfectly in a place where spare parts are rare and expertise is finite. Even if pollination is mastered, the menu remains limited. Early Martian agriculture will not produce mangoes or coffee or citrus groves under alien skies. It will produce whatever offers the highest calories per litre of water, per watt of energy, per square metre of precious pressurized floor space. Potatoes, wheat, soy, spinach, lettuce, maybe algae in tanks bubbling quietly in the background. This narrow diet carries its own risks. Humans are not just engines that burn calories. We are complex biochemical systems that depend on micronutrients, fibre, and a diversity of compounds that interact in ways we still do not fully understand. A colony living for months on a small rotation of fast, efficient crops may meet its calorie targets and still drift into deficiency. Subtle shortages of vitamins, minerals, or essential fats may not be obvious at first. A little more fatigue, slightly slower healing, mood changes. Over time, these small cracks in health can widen. On Earth, variety is often taken for granted. On Mars, it becomes medicine. Beneath all of these challenges, a more mechanical threat waits, silent and patient. The greenhouse is not a field, it is a machine. Pumps hum day and night, circulating water. Filters strain out impurities. Sensors monitor pH, nutrient levels, humidity, temperature, and CO2 concentration. Software adjusts lighting schedules and drip cycles with minute precision. A slight overheat in a controller, a leaking seal in a tank, the failure of a single circulation fan, and months of carefully nurtured growth can vanish in hours. Imagine a power fluctuation during a dust storm that lasts for weeks, cutting available solar energy to a faint red glow. Imagine backup batteries draining just a little faster than expected. Lights dim, pumps slow. The air grows a little colder. To a human, this might mean putting on an extra layer. To young plants, it can mean crossing an invisible line between stressed and dead. In a small colony, redundancy is limited. Spare parts are finite. There is no corner hardware store, no emergency delivery, no overnight shipping. A failed valve during a critical growth phase is not merely an inconvenience. It is a potential turning point in the colony's survival. Every leaf, every tuber, every grain is the endpoint of a vast and fragile system that must operate almost perfectly on a world that offers no help at all. When people imagine failure on Mars, they often picture dramatic events. A suit torn by sharp rock, a hull breach, a storm battering a habitat. Yet one of the most likely paths to collapse is quiet. Calories that dwindle a little too quickly, harvests that arrive a little too late, systems that almost work as well as they need to, but not quite. The impossible farm is not impossible because plants refuse to grow. In theory, with enough technology, enough energy, and enough redundancy, Mars can be made to bloom. It is impossible, at least at first, because everything must work at once. Soil must be purified. Light must be strengthened. Pollination must be orchestrated. Nutrition must be balanced. Machines must run without failing, while humans, under stress and in isolation, learn to become farmers on a world that has never known a forest. In that precarious balance, the first Martian colony does not just grow food. It grows the line between survival and surrender, one fragile harvest at a time. The distance between Earth and Mars is not just measured in miles, it is measured in minutes of silence. On Earth, we are used to voices arriving at the speed of electricity. A tap on a screen, a call placed, and someone answers in less than a heartbeat. Arguments, jokes, reassurances. Our lives are built on conversations that happen in real time. But on Mars, even light, the fastest thing in the universe, becomes slow. When Earth and Mars are at their closest, separated by tens of millions of miles, a radio signal takes about 4 minutes to travel one way. When they are on opposite sides of the Sun, that delay stretches to over 20 minutes each way. A question asked from Mars might not receive an answer from Earth for nearly 3/4 of an hour. A round-trip conversation becomes less a dialogue and more a series of carefully timed monologues sent into the void. Imagine sitting in a small pressurized habitat, half buried in Martian regolith. The sky outside is dim and butterscotch-coloured. Dust curls around your habitat's thin shell like a restless ocean. You open a recording window to send a message home. You see your child's face on a pre-recorded video. They are 6 years old. They are missing their front teeth. They say, "I scored a goal today. Did you see it?" You respond, describing how proud you are, how you watched the delayed footage the night before. You ask them a question. You close the channel. By the time your answer reaches Earth, their day has already passed. By the time their reply arrives on Mars, they have lived an entire week of new experiences. The conversation you are having is with a version of them that no longer exists. On Mars, even love is time-shifted. In the first months of a Mars colony, the novelty might dull the sting. Astronauts train for isolation, for delayed contact, for life inside mission protocols and scheduled uplinks. But a colony is not a mission of months. It is an experiment in permanence. As weeks become seasons, the delay is no longer just a number on the console. It becomes a presence in the room. Silence gains weight. Every transmission window is a ritual. Check the antenna. Align with Earth. Confirm the trajectory of an invisible beam. Then you speak to people who will not hear you for minutes, possibly tens of minutes. You wait for responses that will arrive long after your mood has changed, after the crisis has passed, or after the moment you most needed to hear a specific voice has already slipped away. This is more than an inconvenience. It reshapes the psychology of connection. On the International Space Station, astronauts can talk with mission control in near real time. Something breaks. They describe it. Engineers respond immediately. A valve sticks, a pump fails, a software glitch appears. Solutions can be debugged in conversation. They are never truly alone up there. Earth is in their headset, a constant low-level presence, like a guardian whispering in their ear. On Mars, that guardian becomes a distant echo. A pump fails in the greenhouse. You see humidity dropping, oxygen levels changing on your readouts. The plants that represent months of growth and a significant fraction of your future food supply are suddenly at risk. On Earth, you would call mission control. On Mars, you might still send that message, but you cannot wait for the answer. By the time Earth hears your words, "We've got a failure in the primary circulation line," you have already chosen a course of action. You have already opened valves or shut them, already risked contamination or prioritized one system over another. The advice that returns from Earth will be more like a post-mortem than guidance. They will tell you what you should have done. But on Mars, should always arrives late. In an emergency, the delay is not 20 minutes. It is infinite. Because the only decision that truly matters is the one made in the first few seconds. A fire alarm goes off in the habitat. A pressure sensor reports a leak in the airlock. A crew member is unresponsive on the floor, their suit telemetry spiking into the red. You can inform Earth. You can record your status, send logs, cry out for help. But the reality is harsh and simple. No one is coming through the radio to tell you what to do in time to save a life. On Mars, mission control's role changes. They are no longer controllers. They are archivists, analysts, advisors who speak to a future that has already happened. Their instructions are guidance for the next time, not the current one, if there is a next time. This is where the hidden challenge lies. Our current model of human spaceflight has always assumed a safety net of real-time expertise. Flight surgeons on call, systems engineers watching every sensor, software teams ready to patch code on the fly. A human mission to Mars would carry some of that expertise on board, but it cannot carry all of it. A colony multiplies complexity. It is a small city in a place where nothing outside is survivable. Power systems, life support, agriculture, robotics, mining equipment, medical facilities, recycling loops, communication arrays. Each one is its own discipline. No single crew of a dozen, or even 50, can replace the virtual city of specialists that keeps modern missions alive in low Earth orbit. So autonomy on Mars is not just a buzzword, it is an evolutionary leap in how we do spaceflight. Colonists would need to be more than astronauts. They would be surgeon, engineer, farmer, programmer, psychologists, making critical decisions with incomplete information. They would run simulations, write procedures, and test emergency protocols themselves. And they would have to accept that sometimes they will get it wrong, and no one on Earth will be able to intervene in time to correct them. Complicating this further is the geometry of the solar system itself. Earth and Mars do not politely sit facing each other across a table. They whirl around the sun at different speeds, sometimes drawing close, sometimes drifting far apart, and occasionally slipping behind the sun from one another's perspective. During these alignments, called solar conjunctions, the sun's vast, turbulent atmosphere floods the space between the planets with charged particles and electromagnetic noise. Radio signals, already stretching across millions of miles, pass dangerously close to the solar furnace. Static rises, errors multiply. For safety, mission planners generally accept a hard truth. During certain windows, communication with Mars must be sharply limited or even paused. For days or weeks, a Mars colony could be effectively cut off. No high-rate data, no video calls, no software updates. Only brief, carefully encoded messages, if that. The colony becomes a true island world, its sky empty of voices from home. In those weeks, the silence changes character. It is no longer a delay you can measure on a clock. It is an absence. Earth becomes a star in the distance, visible but unreachable. Even outside conjunction, communication is not the effortless torrent we enjoy on Earth. High bandwidth streaming, cloud backups, instant patches, these are luxuries of a planet wrapped in fiber optics. Between Earth and Mars, every bit of data must be carefully shepherded through deep space networks. Vast radio dishes, limited scheduling, competing missions. A colonist might wait hours for a large software package. Scientific data is not uploaded as a stream, but as a prioritized queue that can take days. A high-definition video call is not a casual possibility. It is a monumental planning event, if it happens at all. The colony will live in an era that feels, in some ways, like a return to the earliest days of the internet. Slow, scheduled, text-heavy, where every megabyte has meaning. This restriction shapes more than convenience. It limits telemedicine, remote diagnostics, real-time collaboration with laboratories on Earth, even the psychological comfort of seeing a familiar face in high resolution. The colony must learn to thrive on partial information and low-resolution contact. To survive this, the people on Mars must become something humanity has rarely been in space: truly self-reliant. Training programs on Earth would need to resemble not a single profession, but an entire university compressed into a human life. Crew members might practice emergency surgeries on advanced mannequins, then switch to running simulated grid failures, then debug life support code, then counsel teammates through panic attacks, all in the same week. Even then, there will be gaps, skills no one on the colony has mastered, decisions they are forced to make by intuition and incomplete protocol. In that gap, between what they know and what they can ask, failure can grow. The communication delay between Earth and Mars is often described as a technical challenge, solvable with better antennas, more powerful transmitters, smarter compression. Those things help. But the deeper challenge is not about hardware. It is about how humans live when the universe itself imposes a pause between question and answer. On the red planet, every conversation with Earth is a message to the past and a reply from the future. That strange stretching of time seeps into daily life, into relationships, into crisis management, into the quiet moments when someone stares at a tiny blue star in the sky and wonders what is happening there right now. For a Mars colony in its fragile first year, that 20-minute silence is not empty. It is filled with responsibility, loneliness, autonomy, and the constant awareness that no matter how advanced the technology, there will be moments when they must face the planet and themselves alone. On Earth, we live inside an invisible safety net. We do not always notice it, but it is there, woven into every city, every town, every quiet stretch of highway. It is the certainty that if something goes wrong with our bodies, somewhere nearby, a light will turn on in an emergency room. A surgeon will scrub in. An ambulance will thread through traffic. Machines the size of rooms will hum to life. On Mars, that net is gone. A Mars colony begins not as a city, but as a compromise. Every kilogram launched into space must be justified. Every tool competes with every pound of food, every battery, every gram of oxygen. In that brutal arithmetic, a fully equipped hospital does not survive the cut. There is no MRI machine, no CT scanner, no intensive care unit. At best, there is a cramped medical bay, a folding exam table, a suitcase-sized ultrasound, a defibrillator, basic diagnostic tools, and a cabinet of supplies that must last not for days, but for years. In this environment, medicine becomes less about fixing everything and more about gambling that nothing catastrophic happens too soon. On Earth, appendicitis is routine, a quick scan, a short surgery, a few days of recovery. On Mars, a swollen appendix is a colony-level crisis. The first crews will almost certainly be carefully screened, their medical histories examined in microscopic detail. But biology does not read mission plans. An inflamed appendix, a twisted bowel, a gallbladder ready to rupture, these are not hypotheticals. Statistically, over a large group of people and enough time, they are inevitabilities. Without a surgical suite, the options are limited and brutal. Powerful antibiotics, strict bed rest, hope that the infection can be contained. A surgery done with improvised tools under conditions that would make any Earthside surgeon hesitate. Sterility becomes a dream, not a guarantee. The red dust that clings to every surface is loaded with perchlorets and potentially with microbes brought accidentally from Earth. In that moment, the colony discovers that on Mars, even a small infection is not a nuisance. It is a predator. Kidney stones, relatively mundane on Earth, become another lurking threat. Dehydration, changes in calcium metabolism, and bone loss in reduced gravity all conspire to make stones more likely. On Earth, a laser, an operating theatre, and a short hospital stay can solve the problem. On Mars, with no operating room and limited imaging, a single obstructing stone can lead to agony, infection, and sepsis, with no straightforward escape. Beneath all of this lies a quieter complication, the way the Martian environment changes the body from the inside out. We evolved under 1 g of gravity. On Mars, gravity is only about a third of that. In orbit, we already see what weightlessness does to astronauts. Bones leach calcium into the bloodstream. Muscles wither without constant resistance. The body begins to forget how to stand. On Mars, colonists will not float, but they also will not bear their full weight. the stress that maintains bone density and muscular strength is diminished. Even with rigorous exercise plans, treadmills, resistance machines, and daily regimens that feel more like training for a competition than living in a home, the body begins to drift away from its Earth-normal state. Hip bones thin. Vertebrae lose mass. A simple fall that might cause a bruise on Earth could mean a fracture on Mars. Healing itself may change. Wounds close more slowly in altered gravity. Blood does not flow and pool in quite the same way. Tissue regeneration might be impaired. A cut hand, a minor burn, a surgical incision. These are not single events, but open negotiations with an environment that does not assist. Every day a wound remains unhealed is another day for infection to take hold in a place where antibiotics are finite and replacements are millions of miles and many months away. Above the colony, another silent force works on the medical system long before any crisis appears. Radiation. Not the dramatic cosmic rays that threaten life support systems, but something subtler. On Earth, medications sit on pharmacy shelves under a blanket of atmosphere and magnetic field. On Mars, even inside habitat walls, background radiation is higher and more penetrating. Medications are molecules, and molecules can be fragile. Over time, radiation can break chemical bonds, slowly degrading drugs. Painkillers, anesthetics, antibiotics, antidepressants, anti-seizure meds. Each depends on precise structure to function correctly. Even a slight breakdown can make them weaker. In extreme cases, degradation could create toxic byproducts. Shelf-lives that were carefully determined under Earth conditions become guesses. A Mars medical officer faces a dilemma unlike anything on Earth. Do you use your precious stock of a life-saving medication early, knowing more might not arrive for years? Or do you ration carefully, hoping that it remains potent while radiation quietly chews at its effectiveness? Pharmacy management on Mars is not bookkeeping. It is probability, chemistry, and ethics tangled together. Then there is the part of health we cannot see on an X-ray, the mind. Long-duration missions in cramped, isolated environments push psychology to its limits. On submarines, in polar stations, and aboard space stations, crews report mood swings, irritability, insomnia, and periods of deep melancholy. These are not signs of weakness. They are signs that the human nervous system is responding to confinement, monotony, and the simple fact that the horizon never changes. On Mars, the stakes of a psychological crisis are higher. If a crew member begins to unravel, anxiety spiraling into panic, depression into paralysis, or pre-existing conditions into psychosis, there is no option to simply send them home. There is no emergency evacuation, no early return flight, no quiet rest in a familiar hospital bed. Psychiatric care becomes an exercise in minimalism, a limited selection of medications, some of which may themselves be degraded, a few virtual reality environments to simulate Earth-like scenes, digital training in cognitive behavioral techniques, group discussions mediated by someone who may only be a part-time counselor, not a full psychiatrist, and always the conversation with Earth that arrives not when you speak, but minutes later. Telemedicine, the idea of doctors on Earth guiding treatment on Mars, sounds like a lifeline. To an extent, it is. Experts can review data, advise on procedures, help interpret lab values and ultrasound images. But physics sets a hard boundary. Depending on the positions of the planets, a message from Earth can take anywhere from about 5 to more than 20 minutes to arrive, and just as long to return. A round-trip exchange that feels like a quick question on Earth becomes a slow-motion dialogue. In an emergency, that delay stretches into something almost existential. A patient's blood pressure crashes. A heart rhythm looks wrong. A wound is bleeding more than expected. The crew can send video, data, desperate questions to Earth. But by the time an answer arrives, the situation will have changed. Telemedicine becomes less like a real-time consultation and more like letters exchanged during a battle. And yet, the greatest challenge might not be a single dramatic event, but the accumulation of smaller ones. A minor injury that heals slowly. A back pain that reveals more serious bone loss. A medication that doesn't seem to work as well as it used to. A crew member whose sleep deteriorates into constant fatigue, then into mood changes, then into conflict that spreads through the group like a quiet contagion. Medical care on Mars is forced into a role it has not played on Earth for a very long time. Medicine without backup. There is no transfer to a bigger hospital, no specialist to helicopter ride away, no dialysis unit in the next building. The colony must become its own last resort. This does not mean a Mars colony is impossible. It means that the first settlers must accept a truth that modern humans have spent centuries trying to escape. Living far from Earth will make us medically fragile again. Preventive care will matter more than ever. Every fall must be avoided. Every small infection must be taken seriously. Every sign of psychological strain must be addressed before it hardens into crisis. On Earth, a hospital is a building. On Mars, the hospital must be the entire colony. Its routines, its vigilance, its willingness to act early and carefully. The danger is not only that there is no hospital to go to, it is that for the first time in generations, we will truly feel the full weight of what it means to be far from help. On Mars, daylight is an illusion of safety. The sun still rises, arcs across the sky, and sets beyond the jagged horizon. But its light arrives thinner, weaker, already diminished by distance. At Earth, a square meter of sunlight delivers about 1,000 watts at noon on a clear day. On Mars, that same square meter receives barely half. Before the first colonist plugs in a single tool, the power grid is already living on a margin. The colony's lifeline begins with solar panels, spread like dark, artificial petals across the rust-coloured plains. Each panel is a promise. Electricity for air pumps, water heaters, greenhouses, computers, medical equipment. Each panel is also a countdown, because Mars has an enemy that never sleeps. Dust. Martian dust is not like the dust on a bookshelf. It is electrostatically clingy, razor-fine, and everywhere. It floats into the air with the slightest disturbance, then settles in a thin, persistent film over everything exposed to the sky. Solar panels that arrived gleaming from the journey quickly grow dull. Their efficiency drops not in sudden catastrophic failures, but in percentages. 2% this week, 3% the next. Small numbers that quietly erode the colony's energy budget. On Earth, a passing rainstorm or a brisk wind often cleans solar arrays for free. Mars offers neither. Rain does not fall here. The atmosphere is too thin for ordinary weather, but just dense enough to lift and carry particles of dust. The colonists can deploy brushes, blowers, electrostatic shakers, even small robots designed to trawl across the panels and sweep them clean. Each solution costs power, time, attention. The grid must pay to maintain itself. Then there are the storms. In 2018, a global dust storm on Mars smothered nearly the entire planet in a reddish haze, darkening the sky for months. The Opportunity rover, which had survived on solar power for 15 years, went silent and never woke up. For a lone rover, that meant the end of a mission. For a human colony, the same event would mean something more severe, the slow suffocation of an ecosystem. Dust storms do not always arrive as planet-wide shrouds. They may begin as local disturbances, regional veils that spread over days. But once a storm grows large enough, sunlight in the affected areas can be reduced to a dim, copper twilight. Under such conditions, solar panels no longer behave like power generators. They become ornaments. Their output plummets to a fraction of normal, sometimes to almost nothing. A colony cannot simply wait out a storm that blocks sunlight for weeks. Every hour, oxygen generators continue to consume power. Habitat heaters draw current to keep the interior above freezing. Pumps must circulate water. Scrubbers must pull carbon dioxide from the air. Computers must coordinate life support. Even sleep on Mars is powered. The power grid is not a convenience. It is metabolism. To survive the long nights and the darker days, the colony turns to storage. Batteries become the second heart of the power system, beating when the sun falls silent. But batteries, too, have their own physics and their own fragility. Mars is cold. At the poles in winter, temperatures can plunge below -120 degrees Celsius. Even near the equator, night can drag the surface down to -80 or -100 degrees Celsius. Lithium-ion batteries, the kind we rely on for phones, cars and satellites, do not thrive in such conditions. Their capacity drops in the cold. Their chemistry slows. Their ability to hold a charge wanes over repeated cycles, especially if they are pushed hard, drained deep at night, refilled in a narrow window of weak daylight. Engineers can bury energy storage underground, tuck it behind layers of insulation, use some of the precious power to gently heat the battery banks and keep their chemistry alive. But every watt spent preserving a battery is a watt not used to run a heater in the crew quarters or a light in the hydroponics bay. Energy on Mars is not just consumed, it is allocated, traded, sacrificed. Over time, batteries degrade. A system that starts with comfortable reserves may, after a year of freezing nights and deep discharge cycles, find its storage shrunk to a shadow of its initial promise. The colony's energy budget becomes increasingly brittle. There is less room for error, less cushion for surprises, less tolerance for storms that last a little longer than expected. This is why, in most serious Mars plans, another power source stands in the background, compact nuclear reactors, quietly humming with a light that does not depend on the sky. Nuclear power on Mars is an alluring idea. A small fission reactor can run day and night, unaffected by weather. It can provide continuous kilowatts or even megawatts of power, a steady river of energy to feed life support, mining rigs, water extraction plants, and greenhouses. But placing a reactor on Mars is not as simple as flipping a switch. First, it must be built on Earth, tested, encapsulated, and launched with extraordinary care. It must survive the vibration of liftoff, the vacuum of space, the heat of entry, descent, and landing onto a world with only a whisper of air to slow it down. Then it must be deployed by machines or crews that have been on Mars only a short time themselves, still learning the terrain, still learning the limits of their own bodies under 1/3 gravity. There are timelines to consider. Some mission architectures propose sending reactors on cargo flights years before humans arrive, allowing the power systems to be tested and stabilized in advance. Others suggest that early crews may rely primarily on solar power, with nuclear units arriving later as the colony grows. In each case, there are windows of vulnerability, periods when redundancy is thin, when a single damaged shipment, a failed deployment, or a malfunctioning core could leave the settlement living on borrowed sunlight. a nuclear reactor must also be cooled. On Earth, rivers, oceans, and thick atmospheres help carry away heat. On Mars, with its tenuous air, rejecting waste heat becomes an engineering challenge of its own. Radiators must sprawl into the cold, radiating infrared energy into the night. Those radiators, in turn, can be coated in dust. In the quiet geometry of a power budget, everything connects. Every subsystem, solar, storage, nuclear, backup fuel cells, feeds into a single question. How much energy is available now, and how long must it last? Heating is the unyielding line item. Human bodies evolved on a warm world, wrapped in a thick blanket of air. On Mars, the air is almost nothing. Heat leaks out through walls, windows, pipes and cables, carried away not only by the thin wind, but radiated directly into space. To keep a modest habitat livable during 100 degrees Celsius nights requires a constant infusion of power. Cut that flow, even partially, and the colony begins to cool, not in cinematic instant freezes, but in slow, dangerous drifts. A few degrees per hour, breath beginning to cloud inside the habitat, water lines creeping toward freezing, electronics ticking down toward temperatures where solder joints crack and screens turn sluggish. This is where cascading failure begins. Imagine the colony's solar output has fallen by 40% due to dust, and the storm forecast extends for another 10 days. Battery reserves are lower than planned, degraded over the past months. The nuclear reactor is still in transit or running at half power while a technical anomaly is investigated. The power allocation board glows with numbers that no longer add up. First, non-critical systems are powered down, exterior science instruments, secondary lighting. Some experiments are put into hibernation. Then the cuts approach the edges of what feels safe. Greenhouse lights are dimmed or run on shortened cycles, stressing crops that are already growing at the edge of viability. Water purification slows. Pump cycles are spaced out further. Maintenance tasks are deferred because the tools required would draw too much current. If the deficit continues, the cuts edge closer to life support itself. Habitat temperatures may be allowed to drop a few degrees to save power, forcing colonists into heavier clothing indoors. Air circulation might be reduced, leading to pockets of higher CO2 and humidity. Batteries are cycled deeper than they were designed to tolerate, accelerating their degradation in order to buy another night of safety. Every compromise sows the seeds for the next problem. Cooler habitats mean more condensation, more stress on seals and materials. Weaker greenhouse lighting means lower yields, tightening the food margin. Deferred maintenance leads to small mechanical failures that later demand emergency repairs at precisely the moment when the colony has the least power to spare. In a system so tightly coupled, the phrase "the grid went down" is not a single event. It is a sequence. One subsystem sags, others overcompensate, and the entire network leans closer to its limits. On Earth, a blackout is an inconvenience, sometimes a tragedy. Crews can be evacuated. Generators can be flown in. On Mars, there is no external grid, no neighboring city, no emergency helicopter ride to safety. There is only the power you brought with you, the power you can generate here, and the thin arithmetic that holds them together. To build a Martian colony is to accept that energy is not merely a tool, it is the first law of survival. Every breath, every sip of water, every bite of food, every message home is an electrical event. A colony fails not only when structures collapse or machines break, but when the invisible river of electrons that flows through its veins slows below a threshold that life can no longer cross. In the deep cold of a Martian night, with the wind whispering dust against the habitat walls and the sun hidden behind a curtain of storm. The colony's future would be measured not in miles travelled or acres claimed, but in kilowatt-hours remaining. In that darkness, the power grid is not infrastructure. It is hope, written in currents and voltages, holding the boundary between a warm, lit pocket of Earth and the frozen, silent world pressing in from every side. On Mars, the horizon stretches wider than anything on Earth. Endless plains of rust-coloured stone, mountains that dwarf Everest, a sky-tinted butterscotone with dust. From the outside, Mars feels vast, open, almost infinite. Inside the habitat, the universe shrinks to a handful of rooms. Walls a few inches thick become the boundary between life and vacuum. Every breath is filtered. Every step is measured. Every door is locked not by choice, but by necessity. The colony, from the inside, is not a frontier. It is a pressure cooker. We often imagine the first Martian settlers as hardy explorers, fearless, driven, immune to doubt. But humans are not just bodies that need air, water, and food. We are minds that need space, variation, privacy, and something that is harder to define. A sense that tomorrow will be different from today. On Mars, that promise begins to erode. The crew wakes up to the same hum of life support fans, the same metallic corridors, the same faces. Outside, a hostile planet. Inside, a handful of people, the same arguments, the same compromises, the same unspoken resentments. Over weeks, then months, the physical risks of Mars become intertwined with a quieter, more insidious danger, the slow unravelling of the human psyche. We do not have to guess how this unfolds. We have rehearsed it, imperfectly, on Earth. In Antarctica, at remote research stations, crews have wintered through months of darkness, sealed off from the rest of the world. There, psychologists have recorded a pattern so common, it has a name. Winter over syndrome. Sleep disturbances, irritability, depression, emotional numbing. Weeks blend into each other like snowdrifts in a whiteout. In analog missions like Mars 500 in Russia, HICs in Hawaii, and Concordia Station on the Antarctic Plateau, small groups have lived for months in isolation, mimicking a Mars mission. Conflicts that seem trivial at first, someone not cleaning up after a meal, a comment said too sharply, a task done the wrong way, slowly grow teeth. In these habitats, there is nowhere to storm off to, no separate apartment across town, no walk in the park to cool down. Anger has nowhere to escape but into the air between people, hanging there, recycled with every breath. One crew member being slightly withdrawn in a city is a personality quirk. On Mars, it is a data point, a risk factor, a potential crack in the only social structure available. Group dynamics in a confined space behave differently than they do on Earth. Alliances form, often unconsciously. Two people grow close, and a third feels excluded. A minor disagreement over procedure slowly morphs into a story about trust, about competence, about who always does this, and who never listens. Every interaction carries more weight because the group is small and the stakes are immense. The person who double-checks everything can be seen either as careful or as distrustful. The person who improvises can be admired for creativity or blamed for recklessness the moment something goes wrong. On Mars, there is no anonymous crowd to absorb our rough edges. Every personality trait is magnified by the pressure of survival. Earth analog studies reveal something else. Psychological breaking points tend not to look dramatic in real time. They creep. The first months are often characterized by high motivation, tight cohesion, a honeymoon phase. Then gradually performance plateaus, irritations accumulate, and communication with mission control can shift from enthusiastic to terse. Sometimes there is a third quarter phenomenon. Not at the beginning when everything is new, and not at the end when home is in sight, but somewhere in the long middle, when the novelty has worn off and the finish line is still too distant to feel real. Morale dips sharply. On Mars, that third quarter might be the 8th month, the 10th, or simply the moment when the colony realizes that the problems are not temporary bugs, but permanent features of Martian life. Layered on top of this is a subtle distortion of time itself. Mars spins more slowly than Earth. A Martian day, a sol, is about 24 hours and 39 minutes long. Only 39 extra minutes. It sounds trivial. It is not. On Earth, our circadian rhythms, the internal clocks that govern sleep, hormones, alertness, are tuned to a 24-hour cycle. Even a few hours of jet lag can cloud our thinking, blur our emotions, and sap our patience. On Mars, settlers will live on a day that is perpetually misaligned with the rhythms their brains evolved to follow. Lights will be programmed to match the Martian soul. Work schedules will slide, bit by bit, relative to an Earth-based clock. Over weeks, some people may adapt, others may not. Sleep becomes lighter, more fragmented. Some will struggle to fall asleep. Others will wake too early, their bodies unsure whether it is night or day. Sleep deprivation is not just about feeling tired. It erodes emotional regulation. It amplifies frustration. It increases the likelihood of conflict. It also degrades decision-making, precisely when decisions must be meticulous and unforgiving. Now imagine adding another layer. You are 140 million miles from home, and the support systems you are used to, friends, family, therapists, casual conversations with strangers, do not exist in any traditional sense. On Earth, a terrible day can be softened by a call to someone who knows you, by a walk in a familiar neighborhood, by the simple ability to be somewhere that is not your workplace, your bedroom, and your emergency shelter all at once. On Mars, going outside means suiting up, managing airlocks, and stepping into an environment that will kill you in minutes without your technology. There are no bookstores, no streets, no cafes, no anonymous benches to sit on and disappear into a crowd. There is only the habitat, the rover, the lab, the same small set of people, the same tasks. Mental health support will exist, but differently. Scheduled telesessions with professionals who are minutes of light speed delay away. Pre-recorded guidance. Training in self-care techniques. These may help, but they do not replace the sheer richness and redundancy of Earth's social fabric. Depression on Mars is not just sadness. It is dangerous inertia in a place where neglecting a simple procedure can ripple into catastrophe. Anxiety is not only an internal storm, it is an overload of vigilance in an environment that is always, genuinely, life-threatening. In such a context, every choice carries more weight. On Earth, we constantly make low-stakes decisions. What to eat, which route to take, when to run errands. They come and go, barely noticed. On Mars, even simple choices are entangled with survival. When to perform maintenance, which system to prioritize, how long to stay outside in a suit before the risk curve starts to rise, how much water to allocate to a crop versus a medical contingency. This constant exposure to consequential decisions breeds a kind of cognitive erosion, decision fatigue. Over time, the brain, always in a heightened state of evaluation, becomes less capable of clear judgment. The mental effort to weigh yet another risk, to choose yet another conservative path, grows heavier. In that state, shortcuts become tempting. Maybe the checklist is skimmed instead of read line by line. Maybe a warning light is assumed to be a sensor glitch just this once. Maybe a crew member's distress is noticed but not addressed because there are more urgent things today. Each small compromise seems harmless in isolation. Under decision fatigue, the line between acceptable risk and dangerous neglect blurs. As months of confinement, misaligned sleep, emotional strain, and cognitive overload accumulate, group cohesion begins to fray in ways that are not always obvious. The colony does not suddenly fall apart in a single argument. It drifts. Shared jokes become rarer. Meals grow quieter. People sit in the same room but feel alone. A subtle us versus them may form between mission control and the crew, or between different roles within the habitat. Engineers versus scientists. Veterans versus first-timers. Those who cope by overworking versus those who cope by withdrawing. In simulations on Earth, researchers have seen communications gradually shift from open, expressive dialogue to clipped, task-focused exchanges. Efficiency on paper, emotional distance in practice. In a fragile environment, that distance matters. When trust erodes, so does the willingness to speak up about small concerns. The very concerns that, if ignored, can evolve into critical failures. The paradox of a Mars colony is that technological success amplifies psychological pressure. If the habitat functions, if life support hums steadily, if the systems do their job, the colonists do not face one big dramatic crisis. They face thousands of small, relentless demands. They survive not a single storm, but a climate of stress that never fully clears. Mars challenges our machines with radiation, dust, and cold. But it challenges our minds with something harder to quantify: the question of how long humans can live as both pioneers and prisoners at the same time. In the end, the first Martian colony may not fail because the air runs out, or the power shuts off, or the crops die in a single catastrophic event. It may fail more quietly, when the invisible bonds that hold a small group together begin to loosen faster than they can be repaired, and the human system, not the hardware, becomes the weakest link. In the thin Martian dawn, the colony looks complete. HAB modules pressurized, solar fields aligned toward a pale sun, life support humming with quiet confidence. On paper, every system has a backup, every risk has a mitigation, every emergency has a flowchart written long before the first footprint touched red dust. But Mars does not read our flowcharts. Unlike a city on Earth, a first-generation Mars settlement is not a web of thousands of overlapping systems. It is a handful of lifelines delicately wired together, each one feeding the next. Oxygen depends on power. Power depends on dust-choked panels or fragile reactors. Water depends on heaters, pumps, filters, storage bladders, and software that decides which valve opens first. Heat depends on insulation that never tears, seals that never crack, and machinery that never pauses. In the comfort of mission design meetings, these are listed as subsystems. On Mars, they are organs in a single body. If one begins to fail, the others do not simply notice, they begin to fail with it. Real missions are rarely destroyed by the big disaster we imagine. More often, they are slowly unmade by a series of small, survivable events that collide at the wrong time. A filter that clogs a little faster than expected. A sensor that begins to drift. A software patch applied one day too late. Alone, each is manageable. Together, they become a cascade, a chain of consequences that accelerates faster than a human crew can respond. Imagine for a moment a future colony entering its 237th sol on Mars. It begins with something almost invisible, almost. Dust accumulation on the solar fields grows slightly worse than predicted during an especially long, hazy period of atmospheric dust. Power production drops by 5%. Not a crisis. The colony dips into its battery reserves more than planned. The crew notes it, adjusts a few non-essential loads, and moves on. But lower power means heaters run a little cooler at night. In one outlying storage module, a waterline approaches a temperature it was never meant to reach. The fluid doesn't freeze completely, but crystals begin to form inside a section of pipe, narrowing the flow path just enough to strain a pump designed with almost no margin. The pump draws more current to maintain its set flow rate. The colony's software sees a spike in demand on a line that is already underpowered. It compensates by briefly throttling other loads, laboratory equipment, charging cycles, even air recycling subsystems. Micro interruptions so short they don't even trigger alarms at first. In the laboratory, one of those split-second power dips interrupts a critical sterilization cycle. A microbial sample, meant to be fully neutralized before waste processing, is only partially inactivated. The system logs the event, but in the bustle of daily operations, the notification sits unread in a queue of minor warnings. Meanwhile, the pump, now running hot, begins to degrade. Its bearings, tested on Earth under perfect conditions, meet the Mars reality of cold starts, micro-vibrations, and tiny dust intrusions each time a panel is opened. Its efficiency drops by a few percent. The software compensates again. More power drawn, more loads shuffled. Days later, the crew notices that water pressure dips briefly every time the greenhouse lighting cycles. They add it to the task list, but every hour is already spoken for. Maintenance on the pump is scheduled for after the weekend, a phrase that on Mars carries an optimism imported from Earth. The partially inactivated biological sample has now moved through the waste stream into a system that recycles and repurposes almost everything. On a closed world, nothing truly leaves. This is the genius of a self-sustaining habitat and its greatest vulnerability. A small, unexpected contaminant can ride the same loops as water, air, and nutrients, appearing days or weeks later in places no one anticipated. By the time the pump finally triggers an alarm, it is no longer just a pump issue, it is a power issue, a thermal issue, a water issue, and a workload issue. The crew diverts their planned scientific schedule to focus on emergency maintenance. Experiments are paused, sleep is shortened, checklists multiply. Psychological strain, until now a background pressure, sharpens. Small interpersonal tensions, held in check by routine, begin to surface under the weight of fatigue and constant urgency. The colony's capacity to respond is not measured only in tools and spare parts, but in human attention. And that attention is finite. As they tear down the pump assembly, they discover micro-cracking in a replacement part that should have lasted years. The analysis is sobering. The part failed not because the model was wrong, but because the model assumed Earth-like conditions of shipping, storage, and handling. On Mars, every crate has been exposed to months of radiation, vibration, and temperature swings during the interplanetary journey, then to a gravity field 1/3 of what all their testing was built upon. The engineering margins that look generous on Earth are suddenly revealed as narrow on Mars. At this moment, the question is not, can we fix the pump, but can we fix it before one of the dependent systems crosses its own invisible threshold? The greenhouse now runs on backup water lines with reduced flow. Plants enter mild stress. Yields weeks from now are quietly lowered by events happening today. This is how a cascade works. The colony is not simply dealing with problems, it is inheriting futures. On Earth, when systems begin to chain together in this way, there is an ultimate safety net: retreat. Ships return to port, planes divert to other airports, expeditions turn back. There is almost always a direction, backward, that leads to more resources, more people, more options. On Mars, the backward direction is measured in months and millions of kilometers. Mission planners run point-of-no-return calculations for the journey between planets. There is a moment, early in the transfer orbit, when turning back to Earth would cost less fuel and time than continuing to Mars. Beyond that point, returning becomes harder than pressing on. It is a clean line drawn in celestial mechanics. For the colony itself, there is a similar threshold, but it is not written in orbital diagrams. It lives in consumables, wear rates, psychological health, and spare parts inventories. How many critical failures can the habitat endure before the crew's ability to repair them decays faster than the systems themselves? At what point does the option to abort the mission and evacuate disappear? Not because the ship home is gone, but because the crew can no longer reach it in a survivable condition. These are not abstract questions. They define the practical limits of early colonization. Even if an emergency return vehicle exists, it is a lifeboat, not a cruise ship. It assumes a crew that is healthy enough, organized enough, and resourced enough to launch. In a true cascade, power instability, water shortages, failing air recyclers, biological contamination, and crew exhaustion converging at once, the point of no return may arrive silently, days or weeks before anyone is ready to admit it. Beyond that line, the colony is committed, not by heroism, but by arithmetic. They must solve their problems where they stand, with what they have. Compounding this is the fragile supply chain stretching back to Earth. A minimum 6-month transit time means that Mars lives in delayed cause and effect. Emergency resupply is not a siren, a helicopter, a convoy of trucks. It is a tiny object launched half a year ago, hoping to arrive roughly where it was aimed. Every bolt, every circuit board, every gram of medicine is chosen years in advance of its moment of need. If the colony discovers a flaw in a critical valve or a miscalculation in the amount of a particular chemical, there is no warehouse to pull from, no neighboring country to borrow supplies. There is only the next launch window and the grim realization that even if the perfect solution leaves Earth tomorrow, Mars will wait through another 2 or 3 seasons before it appears in the sky as a streak of ionized plasma. In this environment, problems do not simply add, they multiply. A failing water pump consumes time that would have been used to maintain air filters. Stressed crew members make slightly poorer decisions, misreading a checklist or delaying an inspection. Power fluctuations, hidden in the noise of one crisis, mask the early signs of another. Each new fire they put out leaves embers in a different corner of the habitat. On Earth, we are used to redundancy that emerges from scale. If one power plant goes offline, a grid of others compensates. If one hospital fills, another accepts overflow. If a city's water supply falters, trucks and trains and pipes from neighboring regions create a buffer. A first Mars colony is not a city, it is a prototype. Redundancy, especially early on, is less about having many systems and more about having single systems designed by humans who tried to imagine everything that could go wrong in a place they have never stood. It is an act of forecasting, constrained by cost, mass, politics, and the limits of imagination. Earth-based contingency planning leans heavily on historical data. We model hurricanes because we have seen them. We improve aviation safety because we have a century of flight records. For Mars, we have a handful of robotic missions and computer simulations. Some failure modes will be anticipated with eerie accuracy. Others will appear for the very first time, not in a lab, but in a habitat where 6 people are trying to sleep. And there is the quiet truth beneath every optimistic rendering of a future Martian city. The learning curve will be paid for in human lives. Every major advance in polar exploration, in deep-sea engineering, in early aviation, came with a ledger of names attached, not because those lives were carelessly spent, but because reality exposed limits that theory could not fully see. Early Mars colonies will be no different. The first crews will live at the sharp edge of our best understanding and our worst blind spots. Some cascades will stop just short of catastrophe, teaching us how to redesign valves, reorder priorities, or rethink crew training. Others will not stop at all. In the long arc of history, these failures may be viewed as steps toward a sustainable human presence on another world. In the short human scale of a single mission, they are tragedies lived moment by moment, with no guarantee that the story will turn upward before the final page. The cascade effect is not a single disaster. It is the revelation that on Mars, survival is not about solving one problem perfectly, but about dancing among many problems at once, each threatening to pull the others down. It reminds us that the first year of a Mars colony will not be a triumphant march into a new era, but a fragile balancing act where every small misstep echoes through systems, through months, and through lives. We leave Mars behind not as a triumphant new home, but as a difficult question mark hanging in the thin red sky. In our first year on this world, we have walked through invisible radiation that slowly unthreads our DNA. We have breathed air that only exists because machinery refuses to stop. We have fought dust that slips past every seal, clogs every filter, and grinds every moving part into failure. We have tried to coax water from buried ice, food from reluctant soil, and electricity from a sun that can vanish behind a planet-wide storm. We have imagined medical crises in a place with no real hospital, only a closet of supplies and a few trained hands. We have listened to messages from Earth arrive not as conversations, but as echoes, delayed by up to 20 minutes, turning urgent questions into slow-motion dialogues. And above it all, we have watched how one loose bolt, one corrupted sensor, one tired decision can start a cascade that threatens an entire colony. Taken together, these challenges do not paint Mars as a welcoming frontier. They describe it more honestly, as a world that does not care if we stay. Yet this is where the story becomes larger than a single year. Every prediction we make about a first Mars colony is bound to a moving target. Radiation shielding may be transformed by new materials or active magnetic fields. Life support systems could become more autonomous, more fault-tolerant, and far more efficient. Closed-loop agriculture might move from barely possible to quietly routine. Technologies that feel experimental now could be standard before the first crew ever leaves Earth. Timelines will shift. Plans will be rewritten. Prototypes will fail, sometimes publicly and painfully. But failure, in this context, is not the end of the story. It is the method. Just as gravity assists turn a fall toward Jupiter into a slingshot to the outer planets, our early missteps become the very force that propels us further. Each flaw we uncover in a habitat design, each underestimated risk, each simulation that ends in disaster on a computer screen instead of on a distant world, is a tiny course correction in humanity's trajectory. The goal of examining how a Mars colony might fail in its first year is not to close the door on Mars. it is to open it carefully, eyes adjusted to the darkness on the other side. A realistic assessment does not weaken our dream of becoming a multi-planet species. It strengthens it by anchoring hope to engineering and imagination to evidence. If you've made it this far, drifting with us through these possibilities in the quiet hours as you fall asleep, you are already part of this long experiment in thinking beyond our own sky. If you found this journey valuable, you can gently tap like so the algorithm knows to send you back here when you need another voyage. You can subscribe to join future expeditions to Europa's hidden oceans, to Titan's methane lakes, and back again to the fragile blue world that still holds all our beginnings. In the comments, let us know where you're listening from. A city glowing at midnight, a small town under clear stars, a dorm room, a hospital ward, a night shift break room. Together, those dots on the map are the first rough sketch of the civilization that may one day reach Mars. And if you'd like to support these long-form journeys even further, there is an optional YouTube membership. It's never required, but deeply appreciated. Another tiny boost to keep this spacecraft of stories powered on. Mars will not welcome us easily. It may reject our first attempts, and perhaps our second and third. But in the quiet between failures, in the careful notes we take, and the lessons we refuse to ignore, progress accumulates, grain by grain, like dust on a red horizon. One day, someone will step outside onto Martian soil, look up at a pale blue star in the sky, and know that entire generations of difficult questions, hard truths, and early failures made that moment possible.